Welcome back to my classroom. Last time you learned first and second derivative test. So quickly review. What's the first derivative test? First derivative is three sentences, right? If original function f is increasing, then first derivative function f prime of x is greater than 0. In the other words, increasing functions slope tangent line is positive. And the backwards working where? So derivative function is greater than 0, which means original function is increasing. And second thing, if original function decreasing, derivative is less than 0. So derivative is less than 0, original function decreasing. And then if fx has maximum point or minimum point, maximum point or minimum point, at that point derivative equals 0 because tangent line of maximum minimum points is 0. We have horizontal tangent line right there. So in the other way, derivative function equals 0, then original function should have maximum or minimum point. Alright, what is the second derivative test? If fx is concaves up, kind of opens up, second derivative is greater than 0, and second derivative greater than 0, the original function must be opens up, which means concave up. And then fx is concave down, then second derivative less than 0. So second derivative less than 0, then original function graph concave down. If original function has inflection points at that point, inflection point was concavity changing point. So at this point, concavity changing from down to up or up to down. If fx has an inflection point, at that point, second derivative is 0. If second derivative equals 0, original function has inflection point. These 6 sentences actually first and second derivative test. So today I'm going to just solve 2 example problems about that. So these 2 example problems really help you to understand more about first and second derivative test. Let's just start from the first example. So just draw the graph of fx equals x cubed minus 3x squared minus 9x plus 5. So how can you draw this function graph? We can draw the function graph using calculator, or we can use x-intercept, which means zeros of that function. But I'm not going to use it that way today. I'll use first and second derivative test to draw this function graph to practice that test. Okay, at first, to draw the function graph using first and second derivative test, we have to know first derivative function and second derivative function because we have to use them. So what is the first derivative function? F prime of x, derivative of this original function, which equals 3x squared minus 3 times 2x, 6x minus 9. Any number's derivatives are always 0. And then what is the second derivative function? Derivative of derivative function. Derivative of this function is x squared derivative of 2x times 3, which equals 6x minus 6. After you got second and first derivative function, find the zeros of those 2 functions. Find the zeros of those 2 functions. So what is the zero of a first derivative function? 3x squared minus 6x minus 3. You can factor this, right? You can factor this like that. 3 x squared minus 2x minus 3. 3 x minus 3 x plus 1. So what is 0 of this function? Negative 1 and 3. We got, and x equals negative 3. Alright. X equals negative 1, 3. These 2 numbers are zeros of first derivative function. What is the second derivative function? 0. 6x minus 6 equals 0? Yeah, definitely 6x minus 1 equals 0. So x equals 1. All right, we got 0 over second derivative function, which equals x equals 1. Fourth step is done. To draw this function graph, I want to use a table. So I hope you to use the same table when you solve these kind of problems. Sometimes some teachers use number lines, but I like table better. So, okay, I'm going to use this table. Step 2. Step 1 is done. Step 1, find the first and second derivative function and then find zeros of those two functions. Step 2. Step 2. I want to use this kind of table. This table has 4 columns. The first column is about x, second column is fourth derivative function, third column is second derivative, and the last column is original function. And then put those 3 zeros we got from fourth and second derivative functions, which are -1, 3, 1. Put these 3 x values in the first column orderly, smallest to biggest. So what is smallest number? -1. What is the biggest number? Positive 3. So now put the numbers -1, positive 1, 3. And then we need to make blank between numbers like that. And then put dot 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 dot. Okay, so you have number lines. So x equals to 1, -1, 1, and 3. That means between -1 and 1. This that means less than -1, like that. Because -1 and 3, those two numbers were 0 of fourth derivative function. So if x equals -1 and x equals 3, fourth derivative function must be 0. Because they are zeros of first derivative function. So what number was 0 of second derivative function? That number was 1. So when x equals to 1, second derivative function is 0. And then you have to fill these 2 lines, first and second derivative function, with signs, positive or negative. Okay? So think about sign in this section. First derivative function is a sign when x is less than -1, like -2, -3. How can you know that? Just plug in the numbers into this first derivative function. I want to use this factored form. It's easier to decide signs. So if x is -2, negative number, right? -5, -2 is -1. So negative times negative will be positive. Okay, that's not going to be positive. Okay, think about fourth derivative function's sign between these 2 zeros, because all these blanks have same signs between zeros. So I want to choose 0 because 0 is between -1 and 3, and then 0 is kind of looks like the easiest number. So if x equals 0, what happens? 0 minus 3, negative. 0 plus 2, plus 1, positive. Negative times positive will be negative. So all those signs will be negative sign. Negative, negative, negative. What happens when x equals greater than 3, like 4? If x equals to 4, positive, positive. So positive. Yeah. We decide all signs for the first derivative function. What about second derivative function sign? Fill out these 6 blanks, but less than 1 and greater than 1. This side has all same sign, that side have all same signs. Because x equals 1 makes second derivative 0. So what about this side? Less than 1, like 0. For the second derivative function, put 0 here. Oh, it's negative. 0 minus 1 is negative, right? So all negative signs for these three blanks. What happens if x is greater than 1, like 2? 2 minus is positive? Yes. All those signs positive, positive, positive. And then think about behavior of function graph of x, fx. So if fx is if f prime of x is positive, and then second derivative is negative, what happened to fx graph? Because f prime of x is positive, where is over here? F prime is positive, right? That is fourth derivative test. If fourth derivative is positive, fx possible increasing. Okay, so that means increasing. Second derivative is negative. Second derivative test. This is second derivative test. If second derivative is negative, then supposed to be concave down. So fx supposed to be increasing concave down. Only possible shape of graph increasing concave down. Increasing concave down will be like that. It's increasing and kind of concave down. The part of concave down. You got it. What is the second thing? If x equals -1, okay, f prime of x equals 0, if fourth derivative is 0, maximum or minimum? But because that's increasing already, minimum is impossible. So maybe maximum, but check next section first before we decide this section. Between -1 and 1, negative, negative. So by the first derivative test, f prime of x negative less than 0, so original function decreasing over here. If second derivative is negative, concave down, so decreasing concave down. So graph should be like that, decreasing concave down. Right now we can know this section surely because they're increasing to decreasing, so that point is maximum point, that's not minimum. Minimum is impossible. Why maximum? Because first derivative equals 0, maximum or minimum. That's not always, but usually. We'll talk about inflection point, whose first derivative equals 0. We'll talk about very soon, but this point is maximum surely. What about x equals 1? X equals 1. That was 0 of second derivative function. That's why 0 is here. So if second derivative function equals 0, that point will be inflection point, concave changing point. So this point is inflection. Between 1 and 3, negative, positive, you know now, right? Decreasing concave up, because positive means concave up. So decreasing concave up. So what is that? Decreasing concave up, this straight. Okay, this is maximum or minimum because the first derivative equals 0. Maybe minimum, right? Double check. So next section first. If x is greater than 3, positive, positive, increasing concave up, increasing concave up. Yes, these kind of things. Wow. In decreasing to increasing, surely this point is what? Minimum point. And then now step 3. Draw function graph using this table. Just before draw the graph, we have to get these values, y values, to draw the graph more exactly. So that means what is y value when x equals -1? So plug in -1 into the original function. This is the original function. If x equals -1, what happens? -1 cubed is -1. -1 squared +1 is -3. -1 times +9 plus 5. So there will be 10 Negative 4 plus 14, that's 10. Oh, that becomes 10. 10. What is y value when x equals 1? Plug in 1 for this x. 1 cube is 1. And negative 3, negative 9, plus 5. So negative 2, negative 11, negative 6. I think negative 6 is right. Yes, right. Okay, what is y value when x equals 3? Plug in 3 for this x, 3 cubed equals 27 minus 27, that will be 0. If x is negative 27 plus 5, that will be negative 22, and negative 22. Now draw the function graph. Using these informations, this is y-axis, this is x-axis, and then just mark these 3 points first. That's easier. If x equals negative 1, y equals 10, over here, 10, that point is a maximum point, max. And then 1, negative 6, 1, negative 6, and then the inflection point, 3, negative 22, over here, that is minimum point. Okay, and then put this shape. If x is less than negative 1, then curve shape should be increasing concave down like that. Alright, so graph should be increasing concave down. Between 1 and negative 1, decreasing concave down in the path of this point. So, and then 1 and 3, this shape, decreasing concave up, the path of that point. And then, if x is greater than 3, increasing concave up, I drew it. That's the perfect fx graph from f prime of x given. I'm sorry, this function is given, and then we're gonna draw original function right now here. I use the first and second derivative test. That's why we had to find the first and derivative functions and zeros of those two functions, and then I made this table because to analyze the function graph, and then I draw the function graph like this. I will give you a bunch of example problem, exercise problem as your homework. So you have to check your homework and then practice for first and second derivative tests using these tables. Let's do second examples. A little different types of problems here. Second example is drawing fx graph using first derivative function graph. Okay, just draw fx graph from f prime of x below. This function graph is given function graph is y equals f prime of x graph. From this graph, we have to estimate. We cannot draw exact location of the function graph. I don't know where it is x-axis for original function graph, but we can draw exact shape of fx graph. So we can just say is estimate original function graph from given f prime of x graph. Let me solve this problem. To solve this problem, to draw original function graph from derivative function graph, at first we have to find two kinds of points in f prime of a function graph. So first type of point is zeros. Zero, what numbers are zeros of this function f prime of? We can know that 1, 10, 15. 1, 10, 15. They are zeros of the function f prime of x, right? And then another type of point we have to use to draw original function graph from given derivative function graph, we need extrema, relative extrema point, which means relative maxima and minima point. Easily maximum, minimum point, right? So, which point is maximum point? This point is maximum, minimum. So we call it relative minimum, relative maximum. What's the meaning of relative? Relative maximum means there's a maximum point because the function graph is increasing, the direction is changed from increasing to decreasing, or that point is minimum point because that function graph direction is changed from decreasing to increasing. So if the function direction is changed, decreasing to increasing or increasing to decreasing, those point is relative extrema, maximum or minimum point. So we have 1, 2, 3 relative extrema point. But that point 10 is what? Relative minimum point at the same time, that point of 0 first derivative function. And it's only 1, 2, 3, 4, 5 points we need to use. I will use these 5 points to draw, to estimate original function graph. I'm going to use same y-axis, and then I'm going to check these 5 numbers, dotted line, I don't know where is x-axis. I don't know. But suppose x-axis is over there, just over here. That doesn't matter. We can't know exactly where x-axis is for original function graph. To know that we need more information. So that doesn't matter. Okay, think about first section when x equals less than 1. Decide. This given function graph is f prime of x function graph. But that graph is under the x-axis, below the x-axis. So that function is negative. And then that function is forced derivative function, which means forced derivative function is negative. Less than. So because the function graph is less than under the x-axis, right? And then this forced derivative function is actually increasing, right? It's increasing. So forced derivative function is increasing. So second derivative function is what? Positive or negative? Let's go back there quickly. I told you original function is increasing, then forced derivative function is positive. Now over there, forced derivative function is increasing. If that forced derivative function is increasing, second derivative must be positive. Let's go back there. That's why, because forced derivative function, the given function, we have forced derivative function, that is increasing, so second derivative is greater than 0. What happened to the original function fx? Because forced derivative function is less than 0, that must be decreasing, and then second derivative is greater than 0, concaves up. Decreasing, concaves up. Decreasing concave, possible function graph is only possible function graph is this decreasing concave up. Decreasing concave up is this. Decreasing concave up. Got it? What about between 1 and 5? Between 1 and 5? Forced derivative function is above the x-axis, right? The function graph is above the x-axis, which means forced derivative function is greater than 0 because above the x-axis, and still increasing. Forced is increasing, which means second is greater than 0. So forced derivative greater than 0 means original function increasing. Second derivative greater means original function concave up. increasing concave up, increasing concave up. That's why the function appears to be like that, increasing concave up. In this interval, right? What about that point? Wow, it looks like a minimum point, right? Yeah, that's right, it's a minimum point because that increasing, that curve direction changed from decreasing to increasing. So that's minimum point, relative minimum. The relative minimum or maximum point, force derivative is 0, right? By first derivative test. Yes, that point is 0. Because force derivative function is 0 at x equals to 1, that point is supposed to be maximum or minimum. In this case, minimum is right. Think about between 5 and 10. What happened for the force derivative function? That graph is above the x-axis or below the x-axis? Above the x-axis, right? So graph then 0, increasing or decreasing? That function decreasing. That's why second derivative is less than 0. So positive and negative, which means fx is what? Increasing concave? Down. Increasing concave down by first and second derivative test. Increasing concave down. And then now think about this point. It looks like an inflection point. Inflection point. Why? Inflection point means what? Concavity changing point. The concavity is changed, right? From up to down. Yes, right. Think about these points. Okay, in this point, force derivative function has maximum point, which means that tangent line slope at this point will be 0. Slope is 0. Slope means derivative, right? That derivative function's derivative is second derivative equals 0 because slope is 0. That's why second derivative equals 0. That's why at that point, ordinary function has inflection point. Think about next section 10 to 13. Still above the x-axis, first derivative is greater than 0. Increasing second derivative is greater than 0. So for the original function, increasing concave up, so function will be like that. This point is very special point because this point is 0 of derivative function. So if force derivative function equals 0, original function has maximum or minimum. But I told you that is not always. There are some special case. This is special case because this is 0 of force derivative function. But if we draw a tangent line, that's still 0. Force derivatives tangent lines will be 0, which means second derivative equals 0. So at x equals 10, actually force derivative and second derivative, both values are 0. In this case, that point is not extrema point anymore. Even though the first derivative function equals 0, if second derivative is 0 as well, that point is inflection, not maximum or minimum point. This is inflection point again. Think about 13 to 15. Above the x-axis, still force derivative is positive, but that's decreasing. So second derivative less than 0. So for the original function, increasing concave down, which means this kind of shape. Increasing concave down. Like that. Think about number 13, x equals 13, this point. At this point, slope is again 0. Second derivative equals 0. That's why inflection. What about x is greater than 15? That graph below the x-axis, that's why force derivative is less than 0. Decreasing, that's why second derivative is less than 0. Negative, negative. decreasing concave down, only possible shape of the function looks like that. That is the maximum, yeah, because the direction is changed from increasing to decreasing. Why? Force derivative function equals 0 at x equals 15. That's why they call it maximum point. Like this, you can draw, you can estimate y equals fx graph from y equals f prime of x graph. So I quickly explain that. If you didn't understand some part, just review and then watch this video one more time, 2 more times, until you understand perfectly this analyze the graph. Okay, I'm done today. Next time I'm going to explain another application of derivatives. That will be motion problem. Motion problem means position and then speed or velocity, acceleration, and their relationship. So we analyze that using derivatives. Thank you guys. I'm done. See you next time.